All right, let's switch to voltage stability. The presentation uses a great analogy here. Voltage is like water pressure in a hose. Too low is a trickle, too high is a damaging blast.
That really captures it well. Voltage needs to stay in a defined range. Too low, things don't work right, motors might stall. Too high, insulation breaks down, equipment gets damaged. Keeping voltage in the zone is crucial.
And the formal definition: the system's ability to maintain acceptable voltages everywhere during normal operation and after events. How is voltage actually managed?
In AC systems, voltage is primarily controlled by balancing reactive power Q, measured in MVARs. Reactive power, doesn't do the work like active power,
Right.
but it's essential for creating the magnetic fields needed to push active power through the network. You need a balance between reactive power supply and demand across the grid.
So what supplies it and what consumes it? The material lists sources and sinks.
Sources include generator excitation systems, their adjustable MVAR sources. Capacitor banks explicitly provide MVARs. And dynamic devices like SVCs and STATCOMs can inject or absorb MVRs very quickly. Sinks are mainly inductive loads, like motors, and also transmission lines themselves consume reactive power when heavily loaded.
Okay.
So voltage stability is about having enough reactive power sources available in the right places to meet the demand and keep voltages up.
The presentation connects this back to the power transfer equation too, saying maintaining V's and VR is needed for power transfer. So voltage affects power flow angle too.
Definitely. Lower voltage reduces Pmax, meaning you need higher angles to transfer the same power, which impacts rotor angle stability. The material shows the typical scenario. Increased load, voltage tends to drop. To counter it, you need to infuse MVAR, add reactive support. Decrease load, voltage might rise too high. You might need reactors to absorb MVIRs.
And there's that graph showing a controllable zone and an uncontrollable zone. What happens if you run out of MVAR support as load keeps climbing?
That's when you risk voltage collapse. It's illustrated on another slide. As load increases and reactive power reserves get depleted or can't reach the problem area, voltage starts sagging. Past a critical point, trying to draw more power causes voltage to plummet uncontrollably.
A positive feedback loop. Lower voltage, more MVAR demand, even lower voltage.
Exactly. It snowballs. Voltage can drop rapidly across a whole region. That's voltage collapse. The curve shows it a gradual decline, then a sharp nosedive.
And the slide on avoiding collapse shows adding reactive support keeps the voltage up, pushing that collapse point further out.
Right. It demonstrates the benefit of having sufficient reactive reserves and deploying them effectively.
What are the main impacts listed for voltage instability?
Well, the big one is voltage collapse leading to blackouts. Also, low voltage scenarios impact loads, cause equipment trips, and voltage problems can definitely trigger or worsen other stability issues like transient or frequency problems. It's all interconnected. And the solutions, they seem to mirror the causes.
Pretty much.
Yeah.
The presentation lists having adequate reactive power resources, both static capacitors reactors and dynamic SVC STATCOMs, using transformer tap changing to adjust local voltages. And as a last resort, under voltage load shedding, UVLS.
UVLS again.
Yeah.
Sounds like the voltage equivalent of UFLS for frequency.
Exactly. It's an emergency protection. If voltage drops below a critical level, UVLS automatically disconnects blocks of load.
To reduce reactive power demand and hopefully stop the voltage from falling further.
Precisely. Sacrifice some load to save the wider system.
Yeah.
The graphs also show how different reactive devices impact the voltage-load relationship, and that voltage collapse typically happens over seconds to minutes, slower than transient, faster than some frequency issues.
Okay, final category presented. Frequency stability, back to generation, and load balance.
Yep, back to the basics. Frequency, the system's pulse rate, directly shows the real-time balance between total generation and total consumption plus losses. Balanced system, stable frequency. Imbalance. Frequency deviates. Too much generation, frequency rises. Too much load, frequency falls. Because the system's rotational energy changes.
Right, that's stored kinetic energy in all the spinning machines. The inertia acts as a buffer, but it can only absorb or supply energy temporarily. Frequency changes reflect changes in that stored energy.
And stopping those frequency changes requires control actions. The material describes 3 layers: primary, secondary, AGC, and tertiary.
This is the standard hierarchy. Primary frequency control is the immediate automatic response. Happens within seconds.
How does it work?
It's usually built into generator governors, their speed controllers, and increasingly into inverter controls. They sense the frequency deviation locally and automatically adjust power output slightly to counteract the change. It's a proportional response, like droop control. Its job is to arrest the initial frequency swing, stop it from going too far too fast. Everyone contributes.
Okay, stabilizes things initially, then secondary control, AGC, kicks in.
Right. Automatic generation control operates over minutes. It's usually centralized within a control area. AGC looks at the frequency error and the power flow deviation on tie lines to neighbors.
Ah, so it manages the area's overall balance.
Exactly. It sends signals to specific generators to adjust their output more deliberately, aiming to bring frequency exactly back to the target value, like 60.00 hertz, and restore the scheduled power exchanges with other areas. It cleans up the error left by primary control.
And tertiary control, that's the slowest layer.
Yeah, tertiary operates over many minutes to hours. It's about longer-term adjustments. Often involves system operators manually instructing plants to start up or shut down, or adjusting schedules for energy storage. Its main goals are to restore the reserves that were used by primary and secondary control, and to re-optimize the generation dispatch for economics, getting the system back to a secure and efficient state.
The material lists the mechanisms: inherent inertia, automatic controls, governor, AGC, emergency, and manual control. It shows a diagram relating power changes, delta P, to frequency changes, delta F, and the control responses over time, and mentions DFDT.
Right, DFDT, rate of change of frequency. That's becoming a bigger concern.
Why?
Because as we replace traditional generators, which have lots of physical inertia, with inverter-based resources, which often have little or none unless specifically controlled to provide it, the total system inertia decreases.
Meaning the frequency change is faster for the same imbalance?
Exactly. Higher DFDT. This puts more stress on protection systems and demands even faster primary frequency response to arrest the frequency deviation quickly.
And the emergency controls are there too, UFLS, under frequency load shedding.
The last line of defense if frequency drops too low, automatically trips load in stages.
And implicitly OFGS, over frequency generation shedding, if it goes too high.
Yes, if frequency skyrockets due to, say, a massive loss of load, tripping some generation might be necessary. The goal is always to prevent a total frequency collapse or runaway. And the material rightly notes frequency control involves both generation actions and, increasingly, demand-side actions, like controlling flexible loads.
Okay, lastly, the presentation briefly covers the tools used to assess all these stability types. What's in the toolkit?
Well, you need good tools to monitor and analyze such a complex beast. The presentation mentions SCADA, DSA tools, offline system study software, and wide area monitoring systems.
WAMS. SCADA, supervisory control, and data acquisition. What's its role?
SCADA is the basic real-time monitoring system. Collects data like voltage, power flow, breaker status from across the grid, usually updating every, say, 4 to 15 seconds, as noted here. Operators use state estimators based on SCADA data, mainly to watch steady-state conditions, making sure things are within normal limits. It's generally too slow for fast dynamics.
Okay, so SCADA gives the big picture snapshot. What about DSA tools?
DSA is Dynamic Security Assessment. These are more sophisticated. They take input from SCADA, maybe PMUs too, and use detailed system models to run simulations in near real time.
What kind of simulations?
They assess dynamic behavior. Operators use them to check the stability impact of potential what-ifs. What if this line trips? What if that generator fails? Would it cause transient instability, voltage problems, oscillations? It helps assess risk based on the current system state.
And the offline system study software, PSSE, Dig Silent Power Factory, PSCAD. These sound like planning tools.
They are. These are powerful simulation packages used by engineers for offline planning and analysis, not real-time control. As described, they use very detailed mathematical models of everything on the grid.
What do they use them for?
Long-term planning, designing system upgrades, planning outages, performing exhaustive contingency analysis, simulating thousands of possible failures, and crucially, determining the safe power transfer limits, ATC-TTC, for key parts of the grid, ensuring all types of stability are maintained under various scenarios. They establish the operational rulebook.
So offline studies define the safe operating boundaries, and SCADA is to help operators stay within them in real time.
That's a good way to think about it. And the final tool mentioned is WAM's Wide Area Monitoring System. The key features highlighted are high-resolution time-synchronized data and real-time system dynamic behavior monitoring.
What's special about WAMS?
WAMS uses PMUs, phasor measurement units. Unlike SCADA's slower updates, PMUs measure voltage and current phasors, magnitude and angle, very rapidly, maybe 25, 30, 60 times per second. And crucially, they are precisely time-stamped using GPS.
So you see things happening simultaneously across the whole grid.
Exactly. You get a high-fidelity, time-synchronized view of the grid's dynamic behavior in real time. You can actually see oscillations propagating, watch angle separation during events, monitor frequency dynamics precisely. It's incredibly valuable for understanding complex dynamics,
Yeah.
especially with lots of IBRs, and for validating the models used in planning in DSA. The material notes large PMU deployments like in India are becoming standard.
Wow. Okay, we have definitely covered a huge amount from this material, from the basics of balance and the power angle, through all the different failure modes, steady state, transient, dynamic, voltage, frequency instability,
Yeah, quite a tour.
and then the tools used to monitor and manage it all. It really gives you an appreciation for the sheer complexity involved in keeping our power grid reliable.
It really does. The presentation shows stability isn't just one thing. It's this multi-layered challenge, balancing physics across different timescales, from millisecond transients to minute-long voltage issues. It's a constant dynamic dance.
Mhm.
And adding all these new inverter-based technologies just adds more layers, new types of interactions to worry about.
It's amazing how interconnected it all is, too. A fault triggers a swing, which causes voltage dips, which might excite an oscillation.
Exactly. One problem can easily cascade into others. Understanding these different stability phenomena and how they interact like this material lays out is absolutely critical for designing and operating reliable grids, especially as we integrate more variable renewables. The grid keeps changing, so studying and managing stability is this ongoing challenge. It needs continuous learning, better tools, smarter controls.
So after going through all this material, here's something to think about. We know inverter-based resources are different. They lack inertia, their response is control-driven. How might the stability challenges of the future grid, one dominated by IBRs, look fundamentally different from the classic synchronous machine-focused problems we've just discussed based on this presentation? What new problems, or maybe even new solutions, does that shift create?
That is the critical question, isn't it? Really gets you thinking about where power system engineering needs to go next.